In lesson 8.6, we are going to be talking about vectors. The speed and direction an object moves can be represented by a vector. So a vector really is something that represents movement. It kind of looks like an arrow on our graph. The speed and direction. Speed and direction, when we refer to that, we're really talking about velocity. So we're representing our velocity with our vector. It says a vector is a quantity that has both length and direction. And it may be a little bit hard to tell, but the symbol for vector is like a bar with half of an arrow. That's the symbol for vector. So this is vector AB. And you'll notice that our vector, if it was graph, this is what it would look like, has a starting point and a finishing point, initial and terminal. We're going to just cover some of the basics first before we look at solving some problems. So the first thing we're going to talk about is the fact that your vector can be named in different ways. It can be named with letters, like we see here, vector AB. It can also be named using component form. And component form of a vector lists the horizontal and vertical change from the initial point to the terminal point. So if I were taking a look over here, I have graphed my vector CD. So this is my starting point is C, my terminal point is D. In component form, I would be looking to show the horizontal and vertical change. And we would do that in these pointy brackets. Horizontal change is 2, vertical change is 3. So in component form, this would be 2, 3. Now, sometimes they're going to give you the starting point and the finishing point, and we need to calculate the horizontal and vertical change. So here, my vector JK, well, the initial point is 6, 0. The terminal point is 1, 3. If we were going to calculate the component form, we need to know that change. Terminal point minus initial point. How much did it change? In component form, then, we would see this would be -5, 3. Which makes sense if you think about your vector being graphed. If your initial point J was at 6, 0 here, and your terminal point K was at 1, 3, roughly here, graphing that, you can see that I'm moving to the left and down. So let's go ahead and take a look at a couple examples there. They're just wanting us to write our vectors in component form. If you looked at example number 1, H is my initial point and G is my terminal point. So I'm looking from the initial to the terminal, my change. Well, I can see I moved to the left and I moved up. So for my vector HG, in component form, I would say -3, 5. My vector MN, well, because M is listed first, this would be my initial point, and this would be my terminal point. If I'm going to calculate in component form, then I need to know the change here. So we're going to take 2 minus -8. I also need my vertical change. I'm going to take -7 minus 1. And we would find, in component form, we would have a change of 10, -8. So that is how you write a vector in component form. Looking at page 2, we can also talk about the length of our vector. The length of your vector is going to refer to the magnitude. Okay, so the magnitude of its vector is its length. Well, on a coordinate plane, if we have something graphed, we know that when we look to find length, we're going to think about using the distance formula. When we're talking about the length, our length is always going to be positive. So when they're referring to the length of your vector or the magnitude, you can see they have it in absolute value because it's going to be a positive number. This is really important. The magnitude of your vector represents the speed of your object. So the longer your vector, the faster your object is moving. In example B, they're going to ask us to draw the vector -1, 5 on our coordinate plane and to find its magnitude to the nearest tenth. So we're really finding its length, which represents its speed. Well, when we draw our vector -1, 5 on the coordinate plane, we are going to start at the origin 0, 0. And we're going to plot that point just like we would -1, 5. So my vector, starting point to initial point, looks as so. If I wanted to think about the magnitude, okay, you might see it written like this when they're asking you to find the magnitude. Well, we know we need the length, and to find our length then, we are going to use the distance formula. We have an initial point of 0, 0 and a terminal point of -1, 5. So if we go ahead and we plug in our numbers, x minus x quantity squared plus y minus y quantity squared, and we need the square root of all of that. I'm going to simplify a little bit here. Looks like my magnitude is going to be the square root of 26, which would be about 5.1. You might see that written magnitude of the vector -1, 5 is about 5.1. Now, because this represents speed, I don't know my units right now, but that could be 5.1 feet per second, meters per minute, something of that nature. When we're talking about the vectors, we can also refer to the direction. The direction of a vector is the angle it makes with a horizontal line. This angle is measured counterclockwise from the positive x-axis. So in my diagram here, this is my positive x-axis. It's measured counterclockwise. And so we may say the direction of vector AB is equal to 60 degrees. But that's not the only way that you can write direction. You can also write the direction of a vector given as a bearing relative to the compass directions, north, south, east, and west. So this vector AB is actually the same one as above, with given as bearing relative to the compass directions, you may see it written as so. Vector AB equal to north 30 degrees east. This and this actually are referring to the same vector. I like to think about this if I were traveling or going north, my vector is 30 degrees east of north. Let's take a look at example C. The force exerted by a skier is given by the vector 1, 4. Draw the vector on the coordinate plane and find the direction of the vector to the nearest degree. So let's start by using our graph. We are going to graph the vector 1, 4. So again, I'm starting at the origin, 1, 4. Now, as I look at this, I'm going to go ahead and call my vector AB. We want to know the direction of our vector. Well, you know what? For us to find the direction, we are actually going to use a little trick. We're going to think about using our SOHCAHTOA. Why is that? Well, if you look, we can go ahead and form a right triangle. And in our right triangle, we actually have legs with a length of 1 and 4. What's my direction? Well, we really are wanting to find my angle in there, my angle X. It's a little hard to see, it's a little squished together, but hopefully my writing is okay. Here I can see, well, I have the opposite side and I have the adjacent side. I need my angle. Well, I could set it up as so. The tangent of x would be equal to opposite over adjacent. Therefore, we know that our angle would be the inverse tangent of 4 over 1. And all we have to do is to calculate. So I'm going to take my calculator. I'm going to take the inverse tangent of 4 divided by 1, which is 4. Now they asked me to round to the nearest degree. It looks like that's going to be about 76 degrees. So here x is about 76 degrees. Well, I want to show you I could write the direction of my vector AB as about 76 degrees. That would be from the positive x-axis. Or I could also write it as a bearing to my compass directions. If this is 76 degrees, would you agree this would be the complement? This would have to be 14. So another way to write that would be that my vector AB would be north 14 degrees east. These two mean the same thing. We can also refer to vectors as either being equal or parallel. If vectors are equal, then they have the same magnitude and direction. It says equal vectors do not have to have the same initial point and starting point, but they would have to have the same length and direction. As they're showing here to the right, that the vector u would be equal to my vector v. Same length, same direction. Down below, vectors can be considered parallel if they have the same direction or they're going in opposite directions. But they may have different magnitudes, so they don't have to be the same length. And equal vectors are always going to be considered parallel. So if we look at example D and we wanted to kind of examine my diagram of vectors here, if I were looking for vectors that were equal, same magnitude, same direction, well, I would see that IJ and OP are equal. I can see if I go over 1 and up 3, over 1 and up 3, that would give me the same length. Vector IJ is equal to OP. Parallel, well, IJ and OP are going to be considered parallel. But also, these two here would be considered parallel. Even though they're going in opposite directions, they're never going to intersect. So vector KL parallel to NN. Okay, we can also talk about taking two vectors and adding them together. When you take two vectors and you add them together, you are getting, or you're finding the resultant vector. The resultant vector, well, when you add them geometrically, if you have them drawn out, add them together, there's two ways that you can look about or think about doing this. Here, if I take my vector u, and I have another vector v, and I add them together, my resultant vector is u plus v. This is their adding head to tail method, one to the other, and my resultant vector would be here in the purple. Another method that you can use is the parallelogram method, where they each have the same initial starting point. So if there was my vector u, and here's my vector v, they're starting in the same point. And I kind of form my parallelogram here. My resultant vector would be the diagonal. Now, when we go through and solve questions today, I'm actually going to show you using the head-to-tail method. I seem to think, or I feel that that's a little bit more commonly used. If your vector is written in component form, we can actually add it numerically. Here, if I were adding numerically my vector u and my vector v, well, you just add your x's together, right over here, and then you take and you add your y's together. Well, let's take a look at an example where we are actually solving a problem, a real-world situation. Now, at this point in class, I'm going to go ahead and take a break and show you the video that our textbook supplies. And they go through an example on the video before we go through and do this on our notes together. You'll see that example video posted on the website. Example E, it says that an airplane is flying at a constant speed of 400 miles per hour at a bearing of north 70 degrees east. A 60-mile-an-hour wind is blowing due north. What are the plane's actual speed and direction? So this is a pretty complicated problem. There's a lot of steps to go through, and I tried to break that down for us as best we can. We're looking for the speed and direction. So step number one, it says the first thing we'd want to do is we'd want to sketch the vectors for the airplane and for the wind. Well, if my airplane is flying at a constant speed of 400 miles per hour at a bearing of north 70 degrees east, if you look down below, the vector for my airplane, north 70 degrees east, I mean if I'm traveling north, I'm 70 degrees east of north. This red segment right here is my vector for my airplane. And if I'm traveling at a speed of 400 miles per hour, well, remember my speed is my magnitude, but speed is also the length. And so that's why my vector is labeled as 400. Now my wind is blowing at 60 miles per hour due north. Due north meaning straight north. And so my vector for my wind is right along here. And again, my speed is my length. And so that has a length of 60. So those are my vectors for my airplane and my wind. Now we know that the wind is going to push our airplane. It's going to affect our travel. And what we're really wanting to find out in the end is what does that do to our speed and direction with that 60-mile-an-hour wind. We want to write these vectors in component form, meaning if I take a look at here, I want to know my x and y values. I want to know the horizontal change and the vertical change. Well, this is a right triangle. Forms there. And again, we're going to use our trig. if I wanted to find my value for x, well, would you agree x is the adjacent side and y is the opposite side, and we have my hypotenuse. So I can go ahead and use SOHCAHTOA. So this technically, I guess, would be step number 2, where we are finding our vector in component form. I'm going to say that the cosine of 20 degrees would be equal to x over 400. And I'm going to solve that for x. I also know that if I wanted to solve for y, I could say the sine of 20 degrees is equal to y over 400. And let's just go ahead and calculate those, and we'll round into the nearest tenth. So about 375.9 and 136.8. So in component form, the vector for my plane would look as so. Now I want to take a look at writing in component form for the wind. Step number 3, writing for the wind. Well, here at 0, 0, and here I am at 0, 60, horizontal change for my wind, well, would you agree we have 0 horizontal change and it is all vertical change? In component form, I would just have 0, 60. Now, step number 4 wants me to sketch the resultant vector and add the components of the airplane and the wind. What would my resultant vector look like? Well, let's just do a rough kind of sketch here. If I had my airplane, my 400 mile per hour airplane, and we know that this vector is 375.9, 136.8, and then I have a wind blowing at 60 miles per hour due north. My resultant vector would be how my plane is actually traveling. My plane is actually traveling along that red line, or that's representing my plane. So in step number 4, we're actually going to take and we're going to add our 2 vectors together. So we are going to take 375.9, 136.8, and we're going to add our 0, 60. This right here is our resultant vector. This is actually telling me, you know, my path is being changed because of my wind. I'm not changing, my horizontal change does not. It remains the same, but my vertical change increases. Well, my resultant vector, this is actually how I'm going to calculate my speed and direction, because I want the length of this red arrow. So those are the numbers that I'm going to use to calculate my speed. So if I come over here in step number 5, and I want to calculate the speed, I know that I want the length, so I'm actually going to do the distance formula. Now, my initial starting point here is 0, 0. So when I take 375.9 minus 0, quantity squared, and 196.8 minus 0, quantity squared, sometimes people don't write those zeros in. I wanted to write those in just so that you were kind of clear on where I was getting my numbers. As you calculate, you take the square root here, and you end up getting about 424.3. What is that? 424.3 what? Well, this is speed. This is actually going to be our miles per hour. So we can see that that wind actually increased our speed, which makes sense because the wind is kind of pushing us along. Now, the final thing that I need to do is I need to think about finding the direction. How did it change my direction? So I'm going to take and just roughly sketch again my resultant vector. Well, I know for my resultant vector that this is 375.9, this is 196.8. And finding our direction then, we actually want to think about finding x. So if we're going to calculate that direction, I know I can use my tangent function. Tangent of 190x would equal 196.8 over 375.9. And I'm just going to go ahead and use the inverse. I can see x comes out to about 28 degrees. Well, what does that mean? Well, that gives me my direction. My direction is about 28 degrees, or we could write that as north 62 degrees east. When you write your directions, a lot of times I'll ask you to write them both ways. Okay, I know those questions can be kind of complicated and kind of a lot of work, but if you stay organized and you follow each step, you should arrive at your final answer. If you have more questions on this, please stop in and see me.